All right. So before we get started, quick announcements. Midterm 2 will take place next Wednesday. So that means I'll finishing 2 more lectures, which is today and Friday, and then everything else won't be on midterm 2. I'll post more information on Canvas announcement sometime soon. All right. And I will be transferring your score from Grayscope to Canvas later today. Once you get that message, do check your grade on Canvas and make sure we did the calculation correct. Okay, so before we move on to the science today, do you have any questions? You can put it on the chat or you can just speak up. No? Okay, sounds good. So for today, we'll start talking about quantum mechanics bounding theories. In specific, sorry, there's somebody want to say something? Okay, never mind. So if you have a question, do speak up. Otherwise, you might want to mute your microphone. Okay, getting started. Today we'll be talking about one of the very useful quantum mechanics bounding theory, which is called molecular orbital theory. And we'll start by talking about the theoretical background of the molecular orbital theory. And then we're going to see some of the applications of the molecular orbital theory in creating correlation diagrams and analyzing chemical bond correspondingly. So before we get started, a quick review on our last Friday's lecture. Remember, we were talking about chemical bonds, right? It's like solving the wave function for the hydrogen atom. By solving the wave function, the Schrodinger equation of H2 plus, which is a 1 electron system, we can consequently get the electronic wave function of H2 plus. So these exact electronic wave function of H2 plus are called exact molecular orbitals. So it's a little bit like atomic orbitals. Molecular orbitals are also solved wave functions. It's a solution of the Schrodinger equation. However, it is almost impossible for us to always solve for the electronic wave function, right? These are complicated differential equations that we cannot solve by hand. So that's why we have 2 different quantum mechanics bounding theories. Today we'll be talking about the first one, which is called the linear combination of atomic orbitals. Are you trying to say something? Otherwise, I might want to just mute you here. Okay, so the first quantum mechanics bounding theory is called linear combination of atomic orbital. Just as its name reads, what we're doing here is by taking the linear combination of different atomic orbitals to give an estimate on what the molecular orbital looks like. So here's what it looks like, right? We have phi MO. So this is the wave function, molecular wave function of the molecule of interest. On the right-hand side, we have 2 different terms. So these 2 terms are the atomic orbital of atom A. And then the right term, that is the atomic orbital of atom B. All right. Just mute people around. So when you're entering, do make sure your microphone is muted. So what we have here is by taking the linear combination of different atomic orbital, you can generate an estimate for what a molecular orbital looks like. And one of the things I want to highlight here is when you're doing the linear combination of the two atomic orbital, it can happen both the constructive way or the destructive fashion. So that's where that plus and minus comes from. And here, CA and CB are the normalization coefficients. Or in another way to put it, is that each of these linear combination of atomic orbital, or LCAOMO, is created from the superposition of different individual atomic orbitals. I know it doesn't make too much sense looking at the equation themselves, so we'll look at some graphical illustration of the LCAO approximation. So we'll start from the simplest scenario, which is the 1s atomic orbital of hydrogen. So this is what the 1s atomic orbital of hydrogen looks like. And this is the graph that we plotted. It's pretty much just the exponential of that negative sigma term. Or if you think about it, right here, we're plotting on the left-hand side, this graph, we're plotting it against the atomic radii. So if we put the nuclei in the center, it is a spherical shape. So the wave function will look like this. Or the other way to put it is sometimes you can also draw just a circle that resembles the 1s atomic orbital. All right, so these drawings are the same. They're just different setup here. So let's think about it. What is going to happen when we have different atomic orbitals at different atoms? And what's going to happen when you put these atomic orbitals in close proximity with each other? So like what we did with the Morse potential, we'll start by looking at we're starting by looking at a scenario where your atom A and atom B are infinitely apart. So here we'll just imagine a H2 where HA is bonded to HB, right? Because it is a hydrogen, so we're always talking about the 1s atomic orbital. And 1s atomic orbital is the spherical shape, or like what we draw here. Right? So when A and B are infinitely apart, what it means is these wave functions do not interfere with each other. Or the other way to put it is each proton, each nuclei will likely hold its own electron. There's no interference. They're just separate atomic orbitals. So that's the first scenario. And then when your atomic distance is coming to the close proximity of your bond length or equilibrium bond length, the wave function of your 1s and 1sa and 1sb, so these are the atomic orbitals of your hydrogen atom A and B, are start to interfere with each other, or these wave functions starts to overlap with each other. Just like anyway, when these two wave functions meet each other, they can interfere with each other in two different ways. The first way is called the constructive interference, where we're creating the new molecular orbital which we call sigma 1s, by the constructive interference of your atomic orbital 1s interfering with the atomic orbital of your atom B. And again, note here, we have a plus sign, so that tells you this is a constructive interference, right? The peak meet the peak. So the consequence here of this construction interference, as you can imagine, the electron density in between, or the density, the probability density in between your two hydrogen atom becomes big. Or if we draw it in the circle fashion, what we have are the two atomic orbitals of the same shade interfering with each other. So what we have here in between the two hydrogen atoms are electron density. And here we have our bonding molecular orbital. Right, so this we discussed last week when we were having electron density in between atoms. That is our bonding molecular orbital. It represents a chemical bond. Alternatively, one could also imagine a destructive interference. So the idea here is almost identical, right? So here we have our new molecular orbital coming from the linear combination of your two atomic orbitals, right? So atomic orbital A and atomic orbital B. And the difference here is this negative sign. That tells you we have a destructive interference. Or what we have is these two waves are of different sign. And when these two waves of different sign meet each other, what it creates is a node plane. Or the other way to draw it is we can draw it in this circle. So this circle means atomic orbital. And then because we have different shades, we have node plane in between. All right, and by definition, node plane, what it means is the low electron density region. Remember, at the node, we have the wave function equals to 0. And consequently, the wave function squared equals to 0. So there's 0 probability of finding the electron at the node and low probability of finding the electron surrounding that node. So the result of these destructive interference are called antibonding, MO. All right. So I'm gonna pause here for like 2 minutes and see if people have questions. I'll also stay after this lecture for another 45 minutes for Q&A. Unfortunately, I'll have to cancel my office hour later today. But nevertheless, so that's the theory part of the molecular orbital theory. And now we're moving on to think about how to use the molecular orbital theory in chemistry, how to better use it to create the energy level diagram, correlation diagram, and how to analyze these correlation diagrams to give you chemical insight. To do that, let's just go over one of the general procedure to construct the linear combination of atomic orbital, the correlation diagram. And at the same time, I'll be drawing on the right-hand side. All right, so on the left-hand side, we have our instruction. And on the right-hand side, you'll see how we use these instructions to create a valid correlation diagram. Okay, so step one. What we have here is we want to construct the LCAO-MO for all valence atomic orbitals. So on the right-hand side, we're looking at H2 here. So what I want to do is first of all, this is an energy diagram. We're talking about hydrogen. So I'm going to write the valence electron and atomic orbital of hydrogen, or the valence electron configuration of hydrogen. So that's 1s1 interacting with 1s1, right? So we're talking about a chemical bond between two hydrogen atoms, and the hydrogen atom's valence electron configuration is 1s1. And then we start to draw the atomic orbitals. And keep in mind, what we have here is if you start from n atomic orbitals, you end up with n molecular orbitals. What it means, on the right-hand side, let's just draw the 1s atomic orbital of my hydrogen atom. Right, so that's what a 1s atomic orbital looks like. On the right-hand side, likewise, you have the same atomic orbital. They're both 1s atomic orbital. They have the exact same energy levels. And the result of these atomic orbitals is the following. For each pair of atomic orbitals interacting with each other, we'll be forming one bonding MO and one anti-bonding MO. So how do we represent a bonding MO? Remember, in the bonding MO, we have the two s atomic orbitals interfering with each other via a constructive fashion. So they're both shaded. So that's a bonding MO, means you have electron density in between the two atoms. Alternatively, you could also have anti-bonding MO, and that has a node plane. That's a result of the destructive interference. So looking at these energy levels, right? So the bonding MOs are more stable than your atomic orbitals. So if we draw here, the bonding MO that's been generated by the constructive interference of the two 1s atomic orbital, that's our sigma 1s. This is lowering energy comparing to our starting atomic orbitals. Alternatively, the anti-bonding MO, or our sigma star, with the node plane is going to be higher in energy comparing to where we start. And then the next step is we can assign electrons into the molecular orbitals. The idea is the same, right? We cannot create or delete electrons just from random. In the H2 example we're showing here, on the left-hand side, we start from 1s electron. On the right-hand side, we also start from 1s electron. And then in the molecular orbital, it means we'll have a total of 2 electrons in H2. And then we use the same Pauli exclusion principle and Hunt rule, which we used in the electron configuration, right? You want to put the electrons in the lowest energy molecular orbitals. So this is how can we create a correlation diagram. It follows 3 steps. The first step is you write out your the first step is to write out the atoms of interest and also their valence electron configuration. All right, and from these valence atomic orbitals, you draw them on the energy diagram and see how they interact with each other. We'll only limit ourselves to bi-atomic molecules for this class. Once you have these atomic orbitals, you start to create molecular orbitals. And the sign here and the rule here to create molecular orbitals is you start from 2 atomic orbitals, you end up with 2 molecular orbitals. These orbitals are not just created from void. You want to make sure the total number match up. Right, so our starts from 2 atomic orbitals. It gives you 2 molecular orbitals. 1 bonding, 1 anti-bonding. And then you put electrons into your molecular orbitals, like what you did with the electron configuration. The last question here is how can we use the constructed molecular orbital? One obvious choice is you can use it to create the electron configuration, the molecular electron configuration. So for H2, the molecular electron configuration is going to be sigma 1s2. Means we have 2 electrons in a sigma 1s bonding molecular orbital. You can also use the molecular orbital diagram to calculate bond order. So by definition, the bond order here equals to 1/2 times number of bonding electron. So that's the number of bonding electron or electrons in the bonding MO minus number of anti-bonding electron. So that's the electron in the anti-bonding MO. So for H2, your bond order equals to 1/2 times number of electron in the bonding MO, which is 2, minus number of electron in the anti-bonding MO, which is 0. And that gives you 1, which is a single bond. At the same time, you can also get information of whether or not this molecule is diamagnetic or paramagnetic. So apparently here in H2, we're predicting both electrons being paired up in your bonding molecular orbital. So we're expecting H2 to be diamagnetic. All right. So how do we feel here? There are lots of information here, but I hope this is a good demonstration in how are we going to do it.
I have a question.
Yes, go ahead.
So how do you know which of the molecular orbitals, sigma 1s or sigma star 1s, to start filling up the electrons?
Right, so these are actually 2 different questions, right? The first question is how do we know if a molecular orbital is a sigma or sigma star? So in this case, sigma means it is a bonding MO. The way we draw it is through the constructive interference. We have electron density, so the hydrogen is going to be here, right? We have electron density in between the atoms, making it a bonding MO. And on the top, when we have the node plan via the destructive interference, it's making it a sigma star or an anti-bonding MO. The second question about putting the electrons there, we're putting the electron based on the energy of these molecular orbital. Like what we did with the atomic orbital, the lower lying molecular orbital got filled up first, right? So in this case, a sigma 1s is lowering energy. We have the y-axis to be an energy. So we put the electron in the lower energy molecular orbital first. And the total number of electrons we can get by looking at the valence electrons available in your starting atoms.
Thank you.
Okay, any other questions? We'll do more examples and then we'll see how that applies.
I had a question.
Yeah, sure, go ahead.
Where did you get the, at the top right of the right screen, where did you get the H of 2 equals sigma 1s squared?
This one? This one is the
Yes.
molecular electron configuration. I may have gone a little bit too fast here. So when we say a molecular electron configuration, it's like our electron configuration. But in this case, we're just talking about in H2, we have 2 electrons lying in your sigma 1s molecular orbitals. So the way I get it, it just reads where my electron is in the correlation diagram.
All right.
Okay, and I see one more question in the chat. It reads, if sigma 1s is constructive, how does it have less energy than sigma star 1s? Yes, that's a good point. So here, remember, we have 2 different ways for the interference to take place, right? So the constructive interference are giving bonding MOs or our sigma 1s. It is lowering energy. So all bonding MOs are lowering energy comparing to your starting atomic orbitals. Alternatively, the anti-bonding molecular orbitals, it has an additional node plan. Whenever you have an extra node, we're expecting that molecular orbital to have higher energy. And in this case, the bonding MOs are always going to be more stable or lowering energy comparing to the atomic orbital, comparing to where we start. And the anti-bonding MO, the sigma star 1s, will always have higher energy. All right, so let's just keep moving and have more time for questions after the class. I have skipped one of the problem here, which is the lithium-2 correlation diagram, but I did add a very detailed walkthrough on the annotated note of lecture 16. You might want to check that out. So moving on to diatomic orbital with p atomic orbitals. Right, so now we're moving on to the second period with both 2s and 2p atomic orbitals being our valence atomic orbitals. I'll use oxygen, O2 here as an example. But before we start creating the correlation diagram, I want to quickly show you how to construct the LCAO MOs from p orbitals. So far, we only talked about the LCAO MOs from s atomic orbitals, and that's quite simple. You just have 2 s atomic orbitals, either it's constructive or destructive. Moving on to the p atomic orbitals, now the drawing of these 2p, of these molecular orbitals coming from p atomic orbitals is a little bit more challenging. So to do that, if you think about it, here are the shapes of our 2p atomic orbitals, right? So if you remember in the Cartesian coordinate, the 2pz aligns along the z-axis, 2px aligns along the x-axis, and 2py aligns along the y-axis. They have this curious dumbbell shape because of the angular nodes that exist in these p atomic orbitals. So to construct the linear combination of atomic orbitals to construct molecular orbitals from these atomic orbitals, what we're doing is essentially the same like what we did with the s atomic orbitals, is to overlap these atomic orbitals in a given way. So on the left-hand side, imagine here are my A and B, and these are my s atomic orbitals. They're just spherical. But in the example of overlapping pz atomic orbitals, let me just copy paste my pz atomic orbital here for your example, for your reference. Right, so we're talking about using the pz atomic orbitals to overlap with each other and construct the molecular orbitals correspondingly. What we're doing here is the same. We just draw the pz atomic orbital like what we did before. This is also pz of A of B. Right, so on the left-hand side, we're talking about a bonding molecular orbital or a sigma 2pz. So pz atomic orbital are just arbitrarily defined to always create the sigma bonds. So in this case, the result of that overlap is effectively the same as drawing it like this. Right, we have bonding MOs, or we have the constructive interference or the high electron density region in between the two atoms. Again, this is a bonding MO because of the electron density in between atoms. All right. Alternatively, you could also create sigma star 2pz or anti-bonding MO. So here's a procedure of creating our sigma star. Likewise, we're drawing our pz atomic orbitals just instead of drawing it via the constructive fashion, now we're drawing it via the destructive fashion. Right, so here we have atomic orbitals of different shape meet each other and creating a node, or the result of this drawing is gonna look like this. So we have an anti-bonding MO, and that's node between atoms. Or when we see node, again, it is by definition a low electron density region in between atoms. So that's for the 2pz atomic orbitals. You can easily imagine we do the same for 2px and 2py. So let me just put a 2px here for your reference. Again, the setup here is the same, right? We have atom A and atom B aligned along the z-axis. So now, if we want to draw my 2px, maybe you can just copy paste it here. Right, so that's our 2px. And I can just move it to that position. Right, so these are my 2px atomic orbitals. And they are interfering with each other via a constructive fashion. Or because of that constructive interference, it's the same as drawing like a lot of electron density on this end. And facing the node plane here, the angular node plane, it's changing its sign. And we call it a bonding molecular orbital because here we have electron density between atoms. All right. And these px and py, the overlap of px and py creates a pi atop molecular orbital. We call it a pi molecular orbital because there exists a node plane, an angular node plane that is containing the axis. All right. And before we move on, we want to draw the anti-bonding molecular orbitals. So the idea here is super simple. You just draw these atomic orbitals and then you align it via the destructive fashion. Or the way we're having here is now we have a new node in between atoms. And that's telling you we have an anti-bonding molecular orbital. This drawing is also equivalent to say, hey, here we have a smaller one, and whatever in the middle is being canceled out. So from the constructive interference of the two px atomic orbitals, we get the pi 2px in the bonding fashion, and also the pi star 2px in the anti-bonding fashion. All right. We'll do this again with the py atomic orbitals. So again, I have my 2py lined up here. What we're doing is we start from these atomic orbitals, and then we put it a line here. So these are my bonding molecular orbitals. The phase matches up. This is constructive. Or it is the same as drawing a molecular orbital like this. And it is a bonding molecular orbital because of the electron density in between the atoms. Alternatively, we could also have the pi star atomic orbital. What that means is we're constructing it, we're having these atomic orbital lined up via a destructive fashion. So we're having an additional node between atoms, meaning this is an anti-bonding molecular orbital. Or more precisely, you can draw it like this. Means the wave function will cancel each other out. So here, I want to quickly summarize my expectation to you, because I do need you to know how to draw the sigma pz, pi px, and pi py molecular orbitals from these p atomic orbitals. All right. And then we can use these newly constructed molecular orbitals of the 2p atomic orbitals to create molecular orbitals, and also the correlation diagram. Before we move on, I want to highlight something, is that the molecular orbitals coming from the 2pz atomic orbitals are generally speaking stronger than the 2px and 2py, because we have more overlap with each other. Remember, in the 2pz, we have the molecular orbital directly pointing towards each other. We have more overlap. So that means we have more stabilizing factor in bonding MO. So as a consequence, we can come up with an energy level diagram of molecular orbitals from the 2p atomic orbitals. Here, let's just use the empty MOs as an example. What we're having is the energy level diagram. Imagine here on the left-hand side, we have px, py, and pz. They're degenerate in energy. What degenerate means is just they're the same energy levels. And on the right-hand side, similarly, we have px, py, and pz. So look at the pz first. These two will interact to form our sigma 2pz. At the same time, it will interact to form a sigma star 2pz. And then the pi 2px and pi 2py are lined in between. Likewise, it has smaller stabilizing factor in 2px and 2py. It also has smaller destabilizing factor in your pi star molecular orbitals. So here is what the energy correlation diagram looks like. Just for empty orbitals, we're not putting electrons in there yet. One thing that we briefly mentioned is that these pi and pi star molecular orbitals are degenerated. Molecular orbitals or degenerated MOs. Okay, so let's look at the MO diagram of oxygen before we move on. So here's a procedure we would like to take if you were asked to draw a MO diagram of O2. You'll do more of these practice in your discussion session. First thing first, write the electron configuration of oxygen. So you should be familiar with it. So that's helium, 2s2, 2p4. So my valence atomic orbitals are the 2s2, 2p4. Quickly sketch it. So 2s will have the spherical shape. You can ignore the radial node when drawing these atomic orbitals. And 2p, depending on where you organize it, that pz, px, and py, right? So I'm using this Cartesian coordinate. And then you can draw the energy level diagram of atomic orbitals. So here are some of the take-home message when creating these energy level diagrams, right? So the number of the MOs you created must equal to the number of starting atomic orbitals. And one pair of atomic orbitals of similar energy will interact to form one bonding and one anti-bonding MO. So what does that look like? So remember, we're talking about oxygen. So what we have is put the energy diagram here. We're talking about the oxygen with valence atomic orbital to be 2s2, 2p4. Same on the right, 2s2, 2p4. The energy level of my 2s atomic orbitals are shown here, 2s and 2p. Right, so the 2p atomic orbitals are degenerated. Also for the right-hand side, that's the same. And in this case, we're talking about each pair of atomic orbitals creating a pair of molecular orbitals. So the pair of 2s gives you sigma 2s and sigma star 2s. So sigma 2s and sigma star 2s come into the 2s atomic orbital of your oxygen atom. For your p atomic orbitals, we just did the same, right? From the 2pz, we have the sigma 2pz and also the sigma star 2pz. That's way up there. And here we have the pi 2px, pi 2py, and the same pi 2px and pi 2py star coming from overlapping of the 2py atomic orbitals. right? And these molecular orbitals coming from p atomic orbital interactions. So it's a sanity check. You want to see how many atomic orbitals we start with. So we start with 4 atomic orbitals on each side. And we end up with 1, 2, 3, 4, 5, 6, 7, 8. 8 molecular orbitals, right? So the total number of orbitals must add up. The next step is to assign electrons into the molecular orbital we created. So in the valence electron of oxygen, we have 2 electrons in 2s, 4 electrons in 2p. On the right-hand side, that's the same. 1, 2, 3, 4, 5, 6. So we have a total of 16 electrons, right? So the 2s goes to the sigma 2s and sigma star 2s, so that's 4. And here we have a total of 8 electrons. So 1, 2, 3, 4, 5, 6, 7, 8. Right, so we've just putting the electron into the lower lying molecular orbitals. So in oxygen, remember when we're talking about the failure of classical bonding theory is that oxygen gas is paramagnetic. And here using the MO theory, we can happily explain the paramagnetism of oxygen gas. We can also calculate the bond order. Remember, bond order equals the number of electrons in the bonding MO. So that is 1/2 times bonding electron, 1, 2, 3, 4, 5, 6, 7, 8, minus electrons in the anti-bonding MO. So 1, 2, 3, 4, minus 4. So the bond order of oxygen equals to 2. Means it is a double bond. All right, so before we end up, so here, you can also deduct the periodic trend for the molecular orbital energy. So that's correlates to the atomic orbital energy. In the same period, what we have in the same period here is that the effective core potential would go up with group number go down. So what that means is the energy of the atomic orbital will decrease. So molecular orbitals created from the lower energy atomic orbitals will also decrease. Or in the other way, in the table, what we are showing here is in general, when we're going from left to the right of the periodic table, we see the molecular orbital energy decrease with group number. We have some peculiar discrepancies here between the sigma 2pz and the pi 2px, pi 2py. So these are a little bit of the extra. I'm not going to test you on this, but if you're interested, you can go to the annotated note and read about it. Right, so that's also Joy's question in the chat, right? Why 2pz is written before 2py and 2px. So that's in this extra time item here. I don't have time to go over it in class today. So as a summary, before we end today's lecture, I also want to remind you there is also a possibility of heteronuclear diatomic molecule to create the MO diagram of HF. So this is also in the annotated notes. I'll also try to record a walkthrough in how to create the MO diagram of HF. That's all the time I have. I will stay on the Zoom for another 40 minutes for our office hour today. And thank you very much for joining. If you have any questions, just stay and I'll answer them.
Hi, I just wanted to double check. You said that the section on the interaction of 2s and 2pz orbitals would not be on the midterm or the final?
No. So this page will not be on midterm or final.
But I'm presuming the heteronuclear diatomic molecules could be.
Yes, this one could be. This one I'll create a walkthrough because I don't have enough time in this class to finish it. And also you'll get practice of these diatomic molecules, the heteronuclear diatomic molecules in the discussion worksheet.
All right, thank you.
Yeah, so this one I'll post a walkthrough. All right. Any questions?
Excuse me?
Yes.
Hello?
Yeah, I can hear you, Alex.
Okay, thank you. Could you go over the bond order and the explanation of how each one is weak and not weak? I was confused on that because, like, you say the bond order you subtract.
Right. So the bond
4.
order and the strength of the bond, the chemical bond, these are two different things. The bond order here, right? What we are calculating is just, let me find some space. So bond order just equals to 1/2 times number of bonding electrons or electrons in the bonding MO minus number of anti-bonding electrons or electrons in the anti-bonding MO. So the equation itself is quite straightforward. What we're doing is just reading the correlation diagram and find where the electron is, right? So in case of oxygen, this is what we did. I'm just gonna circle all the bonding molecular orbital in blue here. So sigma 2s, this is a bonding molecular orbital. Sigma 2pz is a bonding molecular orbital. Pi 2py and pi 2px are all bonding molecular orbitals. So in total, we have 8 electrons in the bonding molecular orbitals. So that's where that 8 comes from. All right, and in the equation, then we're looking at electrons in the anti-bonding molecular orbital. So for example, here we have a sigma star. So that star means it is an anti-bonding MO. And then we have 2 electrons in my pi star molecular orbitals. So in total, we have 4 anti-bonding electrons. So plugging the numbers, we do the calculations, we end up the bond order in oxygen being 2.
And then how does that correlate to how strong or weak it is?
Well, bond order equals to 2 means this is a double bond. So naturally, a double bond is stronger than a single bond.
Oh, okay, got it.
Right. Or if you just want to quickly remember that the bond order, if the bond order is larger, it means you have a stronger bond. All right.
Okay, thank you.
Okay. I read a question from Wendy in the chat. How did you get a total of 16 electrons in the oxygen example? All right, so this is actually quite simple. We just look at the valence electron of oxygen, right? So for each oxygen, you have 2 2s electrons and 4 2p electrons. So that should add up to be 6. I think I have 12. Did I get it wrong? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Yes, that should be 12. That's my bad. That's a typo. Thank you for pointing that out. So that's 6 plus 6 equals to 12. Sorry for that confusion. Next up. Okay, so I'll just stop recording here and I'll post this recording later on along with a walkthrough in how to do the heteronucleic diatomic molecules.